We've been practicing finding the volumes of solids that we form when we revolve a shape, an area, over an axis. And so far, every time we've revolved a shape, it's been around the x-axis. Just notice here, if you wanted some kind of formula, this might be helpful. So if I rotate around the x-axis, I take my slices perpendicular to that axis, which just means I'm taking vertical slices. The thickness of every slice is a dx. And then to show that I'm adding up volumes, volume of a slice shaped like a disc is pi times the radius squared times the thickness. And just notice here, if I'm going to revolve around the x-axis, I'm going to take slices perpendicular to the x-axis. The thickness is a dx, which means I have to integrate with respect to x, at least in first year calculus. We'll talk about some other things you could do later, but in this class, even in second year calculus, we're only going to take slices perpendicular to the axis of revolution. So if the thickness is dx, then I have to integrate with respect to x. So notice that here, I'm saying that the radius is the y value. So radius gets squared, so this y value gets squared. But notice here, I can't actually have that variable y in an integral where I'm integrating with respect to x. So just notice, like on your lab report paper, this is y as a function of x. Just like on your lab paper, step 7, I think, you had to find a formula for the radius as a function of the height. So just imagine that if we took that shape, you did this in your step 9 of your lab report. If we took our shape and instead of revolving around the x-axis, we revolve around the y-axis, we're going to have the same idea. We're going to integrate with respect to y because the thickness of every slice will be a dy. That means the limits on my integral should be y values. That means the radius of every slice is an x distance. So here where this says I'm going to integrate x squared, that x has to be x as a function of y. So here's an example where we're going to revolve around the y-axis. All right, so let's read this. We have a curve, x equals 1 over square root of y. We've been given limits on the y value, and we're told that that shape's going to get revolved around the y-axis. So let's go through our steps. They still work, even if we're going to revolve around a different axis. So here's a sketch of the region. I'm going to shade it a little bit with my light gray color. I'm going to mark the axis of revolution in red. I've been told I'm going to revolve around the y-axis, and I'm going to reflect that region over the axis of revolution. So I'm going to reflect it over the y-axis. It's going to look like this. That's why I call this the lampshade. So I have a better picture in the next slide, but this is what it would look like if I wanted to hand draw it. All right, I blew this picture up really big so we could see it. And let's just remember, okay, I've marked my axis of revolution in red. And I have shaded my region. That's this part over here is the region I started with. The left half of the picture is the reflection. And when I go to draw in my green disc, I said we are going to start your pencil at the axis of revolution, draw through the shaded region, and then back behind the axis of revolution to the far side of the reflection and back toward the axis of revolution. So that's a disc. It wasn't a really super disc. And then I have my axis of revolution sort of went right through here. Because the only question really left to figure out is what is the radius of that green disc? What is the radius of that green disc? So radius. That blue line ends up being horizontal. So how do I find the distance, the length of a horizontal line segment? Well, I just have to find the difference between the two x values because the two y values are equal. So the only distance along this line segment is the horizontal change in distance, so the difference in the x values. And, well, I should make that red. My x-coordinate there was always 0 because that was the y-axis, which is where x equals 0. And my x value there is, oh, it's going to change. You can see, radii should be blue. The radius isn't always the same, but the radius always extends from the line x equals 0, the y-axis, to that blue curve, which we said was 1 over the square root of y. So in this case, my radius is the x distance, and in this case, x is equal to 1 over y. So now I can write my integral. I'm going to integrate with respect to y because I can see that the thickness of my slices, I'm slicing perpendicular to the axis of revolution, which means my slices are horizontal, their thickness is a small change in y. I'm going to have to integrate with respect to y. That's the first decision I make. And this is going to be pi r squared thickness. So pi r squared dy, which means I'm going to have to put y limits on my integral. That's not too bad. I've been very specific about what the y values in this picture are. And what am I going to use in place of radius? I'm going to use the x value, which is given by that function 1 over square root of y. So all I have to do is integrate now. 1 over the square root of y squared just makes 1 over y. This is where I am. So I can find an antiderivative very easily. It's just going to be the natural log of y. Why was it okay that I left off the absolute value bars? Because I'm going to evaluate that integral from 1 to 4. 1 and 4 are both positive. If you're going to be really, really specific, you might like to just keep the habit of keeping the absolute value bars on your y there. So I'm going to get pi times the natural log of 4 minus the natural log of 1. Natural log of 1 is just 0. This is a great answer. Pi natural log of 2 squared or pi natural log of 4. And just notice that if you get excited about the rules of logarithms, you could bring that 2, which is an exponent, to the front. So 2 pi natural log of 2 is another good answer. Any one of these is fine.